Now we move on to horizontal alignment. So you have to take note that the critical aspect of horizontal alignment is the horizontal curve. So the horizontal curve, which focuses on the design of the directional transition of the roadway in horizontal plane. So it is being stated differently that for the horizontal curve, it should provide a transition between two straight lines or tangent section of the roadway. So when you talk about, because horizontal alignment, which is in which the critical aspect is the horizontal curve, and it focuses on the design of directional transition. So the main concern of the directional transition actually is the ability of the vehicle to negotiate a horizontal curve. And according to AASH2, there must be a provision of adequate drainage. So it is important to have in the design for the horizontal alignment. It is unnecessary considering the focus of the design is on the directional transition. So we have the provision of adequate drainage. Now we move on to vehicle cornering. So we talk about vehicle cornering, so which means that handling on a turn, or you make, say, a sharp curved turn on the track by a little oversteering. So that is cornering in a vehicle. So you make a sharp curved turn on the track. So we have here an illustration, a figure showing to us the illustration for forces acting on a vehicle during cornering. So we have here the forces that are acting for a vehicle on a vehicle during cornering. So we have our parameters, our variable. So we have here our R sub V, which is the radius defined to the vehicle's travel. Then we have our F sub C, wherein F sub C is the centripetal force, that is the lateral acceleration multiplied to the mass. Then we have our F sub Cn, which is centripetal force acting normal to the roadway surface. We have our F sub Cp, so that is the centripetal force acting parallel to the roadway surface. And then we have our F sub F, which is the side friction. We have our side frictional force. Then we have our W sub R, which is W sub N. W sub N is the vehicle weight normal to the roadway. So that is the vehicle weight normal to the roadway. Then we have our W sub P, that is the vehicle weight parallel to the roadway surface. So then of course we have our alpha, and that is the angle that it makes with the horizontal for our illustration. That is actually the angle of incline in decrease. So that is those are the forces acting on a vehicle during cornering. So we have here some basic horizontal curve relationship, which can be noted as you have the relationship. You have the formula W sub P plus W sub P plus F sub F is equal to F sub Cp. Then of course we have our equation, which can be written as if F sub F is equal to F sub S quantity W sub N plus F sub Cn. So we can have this equation wherein we have the value of W sub sine alpha plus F sub S multiplied to W cosine alpha plus WV squared all over G times R sub V sine alpha, then equal to W sub V squared all over G R sub V cosine alpha. And we have to take note that our F sub S is the coefficient of side friction, our V is the vehicle speed, our G is gravitational constant, wherein we make use of 32.2 feet per second squared. And of course, if we try to divide both sides of this equation, if we try to divide both sides by W cosine alpha. So which means that we have to divide this by W cosine alpha. So if we divide all this equation or throughout by cosine alpha, W cosine alpha, it gives us this equation. Tangent alpha plus f sub s equal to v squared all over g all over r sub v times 1 minus f sub s tangent alpha. So now, if we're going to have the value for our E, which has our super elevation, so we can have our equation wherein we can set our term f sub s is conservatively set equal to 0 for practical application, and due to the small value of f sub s and alpha, typically assume that this is equivalent to ignoring the normal component of centripetal force. So if we have our E, which is equal to tangent 100 tangent alpha, so we can have our equation be equivalent to this one. We can have our equation for our r sub v. We can have our r sub v equation, which has v squared all over g times quantity f sub s plus e all over 100. Then we have our problem. A roadway is being designed for a speed of 70 miles per hour. At one horizontal curve, it is known that the super elevation is 8% and the coefficient of side friction is 0.10. Determine the minimum radius of curve that will provide for safe vehicle operation. So we are going to solve for the radius of the curve, which is the measured to the travel path. Actually, we're trying to solve for the minimum radius of the curve. So the formula for that is this one: r sub v is equal to v squared all over g times f sub s plus e all over 100. So we have to take note that we are given with we're going to convert, actually we have to convert our mile per hour to feet per second. So if we're going to convert that one, we have to multiply our 70 mile per hour by 5,280 all over 3,600. Actually, if we're going to simplify this one, that is equal to 1.467. So which means that if we try to substitute, so our velocity is the design speed is 70 times 1.467 squared all over our g. Gravitational force is in feet, so we have 32.2 feet per second squared times our f sub s 0.10 plus e all over 100. So that will give us our super elevation E is 0.8 our super elevation is 8%, so over 100. So if we try to simplify, our minimum radius is 1,819. So now we move on to horizontal curve fundamentals. So in connecting straight or tangent section of roadway with a horizontal curve, there are several options available. So which means that we have several options for our horizontal curve. We have 4 options actually. So we have, first one is the simple circular curve, which is just a curve with a single constant radius. Then we have our reverse curve, generally consists of 2 consecutive curves that turn in opposite directions. And we have our compound curves, consists of 2 or more curves, usually circular in succession. It is used to fit horizontal curve to very specific alignment needs, such as interchange ramps, intersection curves, or difficult topography. And the last one is our spiral curve. Spiral curves are curves with continuously changing radius. So these spiral curves are sometimes used to transition a tangent section of roadway to circular curve. So in such case, the radius of the spiral curve is equal to infinity, where it connects to the tangent section and ends with the radius value of the connecting circular curve at the other end. So we have here a table showing to us the minimum radius using limiting values of our super elevation and our side frictional force. So we have our designs. We have to identify the design speed so that we could identify the super elevation and our F's of S. So it is dependent on the design speed that we are after for our E and our F's of S. So we have here our illustration for the different horizontal curves. So we have the simple curve, then we have our compound curve, we have our reverse curve, and of course our spiral curve. So this is these are the option that highway designer can choose from if he is trying to design a horizontal curve. So there are 4 options actually. So these are the illustration for the different horizontal curves. Okay, now we have the figure showing to us, illustrating to us the elements of a simple circular horizontal curve. So we have here our PC. We have PC is the point of the curve. That is actually the beginning point of the curve. So this is our PC, which has the beginning of the curve. Then we have our our PT, which has the point of tangent. Actually, that is the end of the horizontal curve. We have our P sub T. And of course, we have our if we draw a tangent line from our beginning of the curve and at the end of the curve, there is an intersection, which is what we call P sub I. So that is the point of tangent intersection. So from P sub C towards P sub I, actually that is denoted by T, which is the tangent length. So that is the length of the tangent. And from P sub I towards the center of the curve is denoted by our E. So that is the external distance. And from the curve, from the middle curve point towards the line, a horizontal line that connects P sub C and P sub T, that is our middle ordinate denoted by M. And of course, we have our central angle. So this is actually our central angle denoted by delta. So midway to that is delta over 2, and we have our delta all over 2. And of course, from the tangent line towards the horizontal line that connects PC towards PT, that is actually equivalent to delta all over 2. And of course, we have the radius. So we have the radius from the center line towards this point. We have the center line of the road. So from the center line of the road towards PT, and from the center line of the road towards PC, that is our radius. So denoted by our R. So of course, the line from the tangent line, this angle from between the two tangent line is denoted actually by delta. So that is actually equivalent to delta. So that is also is equivalent to our central angle. So we have here we have also an important term to identify. We have what we call the degree of the curve. So actually the degree of the curve is defined as this angle subtended by a 100 feet arc along the horizontal curve, and it is measured of the sharpness of the curve and is frequently used instead of the radius in the construction of the curve. So our degrees of the curve is equivalent to 100 times 180 all over pi all over r, or that is simply equivalent to 18,000 all over pi times r. So we have this is our the degree of the curve. So we have also some geometric and trigonomic analysis. So our t, which is the tangent length, is actually equal to r times tangent of delta all over 2, central angle all over